try and attack that using maximum a posteriori estimation. To mitigate the effect of huge parameter values, we can place a prior distribution P of theta on the parameters. The prior distribution explicitly encodes what parameter values are plausible before having seen any data. For example, we take a Gaussian prior, so P of theta is normally distributed with mean 0, standard deviation 1. We would expect the majority of our values to be on the interval -2 to 2. In fact, we would expect 95% of our data to be on that interval. Once a data set XY is available, instead of maximizing the likelihood, we seek parameters that maximize the posterior distribution, the probability of theta given X and Y. This procedure is called maximum a posteriori, or MAP, estimation. The posterior over the parameters theta, given the training data X and Y, is obtained by applying Bayes' theorem, as P of theta given X and Y is equal to P of Y given X and theta times P of theta over P of Y given X. Since the posterior explicitly depends on the prior parameter P of theta, the prior will have an effect on the parameter vector we find as the maximizer of the posterior. The parameter vector, theta map, that maximizes the posterior is what we call the MAP estimate. To find the MAP estimate, we follow steps that are similar in flavor to the maximum likelihood estimation. We start with the log transform and compute the log posterior as log P of theta given X and Y equals log probability of Y given X and theta plus log P of theta plus a constant, where the constant comprises the terms that are independent of theta. We see that the log posterior is the sum of the log likelihood P of Y given X and theta and the log prior log of P of theta, so that the MAP estimate would be a compromise between the prior and the data-dependent likelihood. To find the MAP estimate, theta map, we minimize the negative log posterior distribution with respect to theta. That is, we solve theta map is in argmin of theta, argmin over theta of negative log P of Y given X and theta minus log P of theta. We can then evaluate the gradient, which is negative the derivative of log P of theta given X and Y with respect to theta, which is equal to negative the derivative log P of Y given X and theta with respect to theta minus the derivative of log P of theta with respect to theta. Notice also that the first term on the right side is the gradient of the negative log likelihood. The conjugate Gaussian prior, probability of theta is equal to normally distributed data with mean 0, standard deviation b squared I. On the parameters theta, the negative log posterior for the linear regression, we obtain the negative log posterior, negative log P of theta given X and Y equals 1 over 2 sigma squared times Y minus B times theta transpose times Y minus B times theta transpose plus 1 over 2B squared theta transpose theta plus a constant. Here the first term corresponds to the contribution from the log likelihood, and the second term originates from the log prior. The gradient of the log posterior with respect to the parameters theta is then given by the derivative, negative the derivative of log of P of theta given X and Y, which is equal to 1 over sigma squared times theta transpose phi transpose times phi minus y transpose times phi plus 1 over b squared theta transpose. Find the map estimate theta map. We take the gradient, set it equal to 0, and solve for theta map. When we do this, we get 1 over sigma squared times theta transpose phi minus y transpose phi plus 1 over b squared theta transpose equals 0. And that's true if and only if theta transpose times 1 over sigma squared phi transpose phi plus 1 over b squared I minus 1 over sigma squared y transpose phi is equal to 0. Moving the last term to the right, we get theta transpose times phi transpose phi plus sigma squared over b squared times I, which is equal to y transpose phi. Taking inverses, right inverses on both sides of the bracketed term, we get theta transpose equals y transpose phi times the inverse of phi transpose phi plus sigma squared over b squared times I. By taking transposes on both sides, we get that theta map is therefore equal to the inverse of phi transpose phi plus sigma squared over b squared times I times phi transpose times y. Couple of notes. Phi transpose phi is symmetric and positive semi-definite. I'll tell you why in a second. You'll also notice that there's an additional term in the bracket, and that's strictly positive definite, so that inverse exists. If we compare this map estimate with the maximum likelihood estimate, we see that the only difference between the two solutions is the addition of the term sigma squared over b squared in the inverse matrix. This term ensures that phi transpose phi plus sigma squared over b squared I is symmetric and positive definite, which means the inverse exists and the map estimate is a unique solution of the system of linear equations. Finally, it's worth noting that that term reflects the impact of the regularizer. Here's an example of map estimates. In the polynomial regression example from before, we place a Gaussian prior on the parameters theta and determine the map estimate. In the figure, we show both the maximum likelihood and the map estimates for polynomials of degree 6 and 8. The prior, or regularizer, does not play a significant role in the low-degree polynomial on the left. But for the higher degree polynomial on the right, it keeps the function relatively smooth. Although the map estimate can push the boundaries of overfitting, it's not a general solution to the problem. So we need a more principled approach to tackle overfitting. In the next video, we'll learn a little bit more about regularization and the regularizer.